Hey everyone, and welcome. Today we are diving into a really powerful machine learning technique, one that doesn't just predict things, but actually simplifies them. We're talking about lasso regression, and you're about to see how it basically becomes a minimalist for your data.
But let's kick things off with a big question. We live in a world that's just swimming in data. So how can a model be smart enough to figure out which pieces of that data are actually important and which parts are just noise? Well, that is the exact problem that Lasso was designed to solve.
So to really get why Lasso is so cool, we first have to understand the problem it's fixing. The idea that more data is always better can actually get a model into a lot of trouble. It leads to a classic issue called overfitting. Think of it like this. An overfit model is like a student who just memorizes the exact answers for one specific test. They'll ace that test, but if you give them a new set of questions on the same topic, they can't apply what they've learned. The model gets really good at explaining the past data, but it's terrible at predicting the future. And predicting the future is the whole point.
Okay, here's a fantastic way to picture this. Imagine you're packing for a trip. A standard linear regression model, that's the packer who just throws their entire closet into the suitcase. Lasso, though, is a minimalist. It picks up every single item, every feature in your data, and it asks, do I really need this? And if the answer is no, it gets left behind.
So how does Lasso pull off this minimalist trick? Well, the secret sauce is something called the L1 penalty. If you look at the formula, the model isn't just trying to reduce its prediction error, it's also adding a penalty that's based on the sum of the absolute values of all the feature weights. This basically encourages the model to be more efficient, to get the job done by using fewer, more important features. And that L1 penalty is what makes Lasso so incredibly powerful. Using the absolute value creates this really interesting mathematical effect. You can think of it like having sharp corners in the problem it's trying to solve. And because of those sharp corners, the easiest way for the model to minimize its total cost is often to just squash the coefficients of unimportant features all the way down to exactly 0. It doesn't just shrink them, it totally eliminates them. It's doing automatic feature selection for you. All right, that's enough theory for now. Let's see how this thing actually works in practice. We're going to build a lasso model from the ground up, right here in Python, using a real-world dataset to predict the progression of diabetes. Okay, first things first, we've got to import our tools. We're bringing in NumPy and Pandas for all our data manipulation. Then, from the amazing scikit-learn library, we're grabbing the diabetes dataset, a function to split our data for training and testing, a standard scaler for pre-processing, and of course, the stars of our show, linear regression, ridge, and lasso. So, we're using this built-in diabetes dataset from scikit-learn. This code here loads it up and neatly organizes it into a Pandas data frame, which is way easier to work with. We've got 10 input features, things like age, BMI, blood pressure, and our goal is to predict how the disease will progress a year later. Then we use the .head function to just print out the first few rows to get a quick look at our data. And here's a little snapshot of what we're working with. You can see all the features like age, sex, and BMI. Now, this particular dataset already has its features scaled, but I want to stop here for a second, because scaling is an absolutely crucial step for any model that uses regularization, and here's why. This is so important. Regularization works by penalizing the size of the model's coefficients. So, if you have one feature that ranges from 0 to a million, and another one that ranges from 0 to 1, the model is going to unfairly punish the feature with the bigger numbers. Scaling puts every feature on a level playing field, so the penalty is applied fairly. And here's the code that does exactly that. We use train-test-split to slice our data into training and testing chunks. Then we create an instance of the standard scaler. Now pay attention here. We use .fit transform only on the training data. This learns the scaling rules and applies them. Then we use just .transform on the test data to apply those same rules. This prevents any information from the test set from leaking into our training process. Okay, now for the main event. Our data is prepped and ready to go. So let's train 3 different models: a standard linear regression, a ridge regression, and of course, lasso. This is going to let us see side by side exactly what makes lasso so different. First up, we need a baseline. So we're training a plain vanilla linear regression model. We just initialize it, we fit it to our scaled training data, and then we make predictions on the test set. There's no regularization here, no penalties. It's going to use all 10 features no matter what. This is our starting point. And what do we get? An R-squared score of about 0.45. In simple terms, this means our baseline model can explain about 45% of the variation in the data. That's not bad. But the question is, can we do better by being a little smarter about our features? Next, we bring in the contenders. We're training a ridge model, which uses that L2 penalty. It squares the coefficients. And then we train our star, LASSO, with its L1 absolute value penalty. For both of them, you'll see this alpha parameter set to 1.0. You can think of alpha as the knob that controls how strong the penalty is.
And the results are in. And this is really interesting. Take a look. LASSO actually achieves the highest R-squared score of the three. This is a huge deal. It suggests that by simplifying the model, by actively ignoring some of the noise, it actually made a more accurate and robust prediction. Let's see how it did it. Okay, this right here. This is the magic of LASSO. Just compare the coefficient columns. Linear regression and ridge have assigned some value, some weight to every single feature. But look at LASSO's column. The coefficients for features S1 and S2 have been shrunk to exactly 0. LASSO has looked at the data and said, you know what? These two features aren't helping, and it just completely removed them from the equation. This bar chart just makes that difference impossible to miss. Linear and ridge regression, they kept all 10 of the original features. But LASSO created what we call a sparse model. It got rid of 3 features completely, keeping only the 7 that it decided were the most predictive. That is automatic feature selection in action. So you might be wondering, okay, how do we control how aggressive LASSO is? Can we make it remove more features or fewer? And the answer is yes. The key is that hyperparameter we saw earlier called alpha. Think of it as a knob you can turn to control that balance between a complex model and a simple one. Yeah, alpha is basically the simplicity knob. If you turn alpha way down, the penalty is really weak, and LASSO will act almost exactly like a standard linear regression model. But if you crank alpha way up, the penalty gets really strong, and it can force too many coefficients to 0, making the model too simple, which we call underfitting. Finding that sweet spot for alpha is the name of the game. So let's wrap this all up. What are the big takeaways here? LASSO is your best friend when you have a ton of features and you suspect that a lot of them are probably just noise. It simplifies your model, which makes it way easier to explain, and as we saw, it can even boost performance by forcing the model to focus only on what truly matters. And please, please remember, always scale your data first. Here's a great little rule of thumb to keep in your back pocket. If you think most of your features are probably useful, but they might be highly correlated, ridge is a great choice to just stabilize things. But if you want a clean house, if you want to find the few golden nuggets that are truly driving the outcome, LASSO is the tool you want. And that's our deep dive into LASSO Regression. You see, it's so much more than just a prediction tool. It's an explanation tool. It forces you to ask not just what your model can predict, but what are the really important drivers behind those predictions. So the real question is, what will it reveal when you point it at your data?
Like and subscribe for SimplfyTech, explaining one concept at a time, simplifying the technology and AI.